So I welcome you all in this session where we will have some kind of interaction later on. And uh, the idea is that I will pass on the idea of dark matter and dark energy to the audience. And then the moment we will have that brief presentation on this title, then we will go with some of the basic questions of the cosmos, of the universe. And before we go into the details of this presentation, and we have a clarity, at least in classical world, classical physics, that's based on Newtonian mechanics. And we rightly understand that Newton's universal law of gravitation is purely applicable to the solar system in which we are living in a planet known as Earth. Now, if we use this universal law of gravitation, it purely explains us the motion of planets, the motions of the moons with respect to their planets. Uh, and universal law of gravitation also tells us that the planets which are very away from the sun, their speeds are lesser. Okay, so we can say that Earth is moving with the more speed than that of the Jupiter, because Jupiter is farther than that of the Earth. So this physics is working. It's not the wrong physics. It's purely the right physics. Even we use Newton's laws of motion and Newton's gravitational laws to send the rockets on the moon. We send things on the other planets like Mars using Newtonian laws, universal law of gravitation. So this point is clear that that when you seek the information about the solar system, universal law of gravitation is purely predictable. It completely predicts the motion of the planets, except a few, the like of Mercury. It does not purely explain that, because then comes the general theory of relativity, because general theory of relativity gives us the pure explanation of the motion of Mercury. Now, the first point is that what is dark matter? Okay, and then the next question is what's dark energy? So these are two different things that are existing in the universe. We have not yet confirmed them experimentally, but the mathematics tells us that these things should exist in the observable universe. Now, the point is that what we start with is the dark matter. Okay. Now, what's the dark matter? So, dark matter is something which has complete gravitational attraction in it. Okay. It exactly attracts the objects the way Earth attracts an object. But the point is, it is dark because it does not interact with the electromagnetic radiation. So if it does not interact with the electromagnetic radiation, you cannot see it. Interaction with the electromagnetic radiation means it does not absorb the light. If it doesn't absorb the light, it will not emit the light. Are you getting my point? So from electromagnetic point of view, this matter should not be visible to us through any means directly. Okay? Because it's only the light or electromagnetic radiation that interacts with the object and we can see it. I can see you. Why can I see you? I can see you because of the light falling on your faces, reflecting back from your faces, hitting my retina, reaching to my brain, and I'm able to see you. No doubt it takes a very, very short span of time. The mechanism is something like this. So the dark matter and dark energy, they are the two biggest mysteries in the modern in the modern physics. I should say modern cosmology, if we point it out to the cosmologists, because they are observing the universe in the night. Getting my point? Okay. So what I said dark matter, okay, does not interact with the light, but it has complete gravitational action involved in it. So it is attracting, okay? The way ordinary matter attracts, in the similar way dark matter attracts. Again, it's an invisible matter, okay? That does not emit or absorb light, but it exerts the gravitational effect. So you can sense them only through the gravitational effects. They can tell you that, come on, there must be something that is attracting that object, right? So this is the point till now. Now, these are the three important things. I mean, what are the evidences that there should exist the dark matter in the universe? Okay? There has to have the evidence. And if you rightly remember, as I started this presentation, I talked about the solar system. I talked about the universal law of gravitation. And we could easily estimate the first thing, that anything that's moving away from the center, its speed should be less. Clear? So here, the evidence for the dark matter. The very first thing is galaxy rotation curves. Now you have telescopes, the Hubble telescope, James Webb telescopes. You are seeing the sky through electromagnetic radiations, okay? And you are seeing the motion of the stars in the Milky Way, right? Now, what happens, what strange happens is, when I see the stars close to the center of the galaxy, they have a speed. The way Earth has a speed with which it's moving with respect to the central mass. Getting my point? And I do the same analysis on a star which is on the periphery of the galaxy. What should I expect? I should expect their speeds should be less than that of the speeds of those stars which are close to the center of the galaxy. But what we observe a totally different thing. We observe that the stars, the interstellar matter that is on the periphery of the galaxy, it has the same speed as that of the stars that are close to the center of the galaxy. So universal law of gravitation is not working. Okay? It's not working. Now how can I compensate this thing? Here in the solar system, it works. But when I apply it to the galaxy, it doesn't work. Now what should be the reasons that the speed of the stars that are on the periphery, their speeds are same as that of the stars that are close to the center of this galaxy? We come up with an idea of dark matter. We say, come on, in those regions of the galaxy, there must exist dark matter. Because maybe that dark matter, which is not visible to us, is attracting those stars, and the speeds of these stars are same as that of the speed of the star which is close to the center of the black hole. Are you getting my point? So it's the very first explanation that we give mathematically. If you rightly remember, I'll go with that. Okay. So the point is here that galaxy rotation curves are an indication of the existence of the dark matter. Now, another important thing is gravitational lensing. Last time we talked about the black holes, okay? And we said they are highly dense objects in the universe. They warp the space-time. The warping of the space-time is such, even light particles cannot escape. So light particles cannot escape means the gravity has an influence on the light particles. The gravity has an influence on the... So that means if I have some object here, say for example, Say I have a star, for example. It has a mass, tremendous mass. It has gravity. Okay. Now I will see the light passing via this star. Okay. What do you expect to the light as it passes close to the star? You expect it will bend. This is what you expect because of space-time curvature. If you have a tremendous gravity, it will impact the trajectory of the light. Okay? Now, what these cosmologists do in the laboratories, they see the gravitational lensing. They see the light passing to a nearby star, and they calculate the bending of the light. When they calculate the bending of the light, what they obtain is that the bending that they obtain in their light happens to be more than that of the mass that is available to them. Are you getting my point? Okay, you have this much of mass, you have light, the bending, say for the sake of argument, the bending should go to 30 degrees. Say for the sake of argument. Okay? But when I calculate this bending with the same mass, I find that the bending is 45 degrees. Say for the sake of argument. Now there's a problem, because you are calculating a bending which is giving you the more angle. Now what could be the reasons? Dark matter. So what they do, they add the dark matter to that region, okay, wherefrom they have measured the gravitational lensing. They add that matter and they are able to explain that why the light bends to 45 degrees, right? But the observable mass, observable is only that which emits light. You cannot see anything which does not emit light. I can't see you if you don't reflect the light. You will be just invisible to me. Getting my point? So this is how gravitational lensing gives us an indication that there is existence of what?
Dark matter.
Dark matter. Are you getting my point? Okay. Now this CMBR, this is called cosmic microwave background radiation. This thing was it was discovered in 1965. And let me start with, do you remember our televisions? When our televisions used to have no signals? You used to find those dots on the television. Even today we can find them. That is CMBR, cosmic microwave background radiations. And what is it? It is the sound. It is the radiation that was emitted at the time of Big Bang. Right? These radiations are still present in the universe. They are the part of this universe. Okay? And these radiations were discovered in 1965. And this is another evidence when we measure those radiations, microwaves that are present in the universe. They give us different scales of temperature of the universe. They tell us a lot about the universe. But we are able to complete this theory only when we attribute not only the dark matter, but also the dark energy, which we'll be talking in a moment. So CMBR is another indirect evidence of existence of. Now these are all indirect evidences, okay? So the point is, these are the evidences that are available to us. So this thing I think I have explained to you. Galaxy rotation curves, okay? As I said, what it says, stars at the edges of the galaxies, they rotate faster than they expected, okay? And this implying that there is some unseen mass. That's why they have the greater speeds, and their speeds are as equivalent to that of the stars that are close to the center of the galaxy. Are you getting my point? Gravitational lensing, I talked about it, I explained it. So light from the distant galaxies bends more than the visible matter. Okay? This accounts for there must be the dark matter, because the bending that you are calculating with respect to that galaxy, okay, that you see in the Hubble images, that bending is more. So you can explain that bending only if you incorporate the additional invisible mass to the galaxy. Clear? CMB evidence, as I talked about, tiny fluctuations in the CMB shows the effects of dark matter on early universe structure. Because that is the radiation available to us that's there. What happened 13.7 billion years ago, that disturbance is present in the universe and you can measure it. So there are these important candidates for dark matter. WIMPs is one of them, weakly interacting massive particles. Even though they are hypothetical in nature, we think about them in terms of particle physics. Axions are another set of particles which we attribute that these particles may be the part of the dark matter. Machos. And machos are your black holes and neutron stars, which we also call as pulsars. But machos alone do not contribute to the whole of the dark matter. So if you have black holes and neutron stars, they don't account for the dark matter that's present in the observable universe. So certainly there has to have some other particles which we have not even encountered, which are yet to be discovered to account for the dark matter in the universe. Now is the next thing. So dark matter is over. Okay, the basic idea is clear. Now the point is, when the Hubble is looking at the galaxies, he finds a shift, which is called a redshift. Redshift is something you might have learned in your previous classes about Doppler effect. Doppler effect in terms of sound. The effect gives you an idea whether an object is moving towards you or the object is moving away from you, right? Now, replacing the sound by an electromagnetic wave, you can actually calculate which of the galaxies are coming towards us and which of the galaxies are going away from us. Now, when the galaxies go away from us, we call it redshift, okay? And if the galaxies are coming towards us, we call it blue shift. But most of the galaxies that we observe in the universe, they show us the redshift. Now what does it mean? It means universe is expanding. Now universe is expanding, it's against the basic understanding of the physics to us. I mean, if you have two objects, they're bound to each other. How they are bound? They are gravitationally bound to each other. And if you bring them close to each other, the force between them is going to increase. But if you take them away from each other, the force between these two bodies is going to decrease. So what will happen to what should happen to the expansion? The expansion should stop at some point. It should not go on. It should go on. Because if galaxies are moving away from each other, and they are not only moving, they are moving faster. Even it's attributed that there are galaxies which are moving with the speed greater than that of the speed of the light. So how is it possible? If you have an explosion, the matter is going on. For the sake of argument, the gravitational force should weaken. And finally, it should end. In fact, the reverse should happen now. Now these balls should come back. There should be the contraction of the universe. But what they are observing? They are observing that galaxies are moving. They are moving very, very fast. And you cannot account for that. You cannot account the dark matter, because dark matter is what? It is an attractive matter. It has a gravitational attraction in it. So you come up with an idea of dark energy. You know, Einstein once, in explaining the universe, because Einstein believed that universe is static. And why it is static, he had to add a constant in his equation. That constant is called as cosmological constant, to explain the stability of the universe. But later on, from observation's point of view, he said, come on, I did the bad thing. Do you remember the story of the horse? God sitting in the heaven. Einstein in the similar way said that it was a wrong idea to use the cosmological constant. But now, the cosmological constant has been again introduced, but in a different way. We again call it cosmological constant in cosmology. Now what they say, come on, universe is filled with something known as dark energy. And this dark energy is not an attractive energy, it's a repulsive energy. And majority of the universe is filled with dark energy. Are you getting my point? So dark energy is something that you add to your equation to explain the expansion of the universe. Otherwise, the equations that you have developed till now, they will not work to explain the universe. Because if you talk of the universal law of gravitation, it works in the solar system. It doesn't work in the galaxy. And it doesn't at all work with the expansion of the universe. It's a wrong equation. It's not giving you the correct answer. Now to keep that equation right, what you do? You introduce a constant, you introduce an energy, and you call this energy as? So it's a mysterious energy. We have not detected. But it gives it signatures because the universe is expanding. So a mysterious form of energy causing accelerated expansion of the universe. Based on observations, as I said, of the distant types of supernova, they are another candidates to understand the expansion of the universe. Evidences, accelerated expansion, large-scale structures, the data that you have, cosmic microwave background data, they are all pointing towards the existence of dark energy. And come on, this energy is what? It's a repulsive energy. It is going against the gravitational attraction of the dark matter. Okay? It's going against that and it's winning the war. That's why its percentage should be large. Its percentage should be large in comparison to the visible matter and the dark matter. As I said, Einstein's cosmological constant is a candidate explanation for the dark energy. But I said you the story of this. At the first, when it was assumed that the universe is static, standard model, in standard model, Einstein introduced this cosmological constant. Then he removed it from his equations. But later on, people had to incorporate, they incorporated it, but with different means. It gives you the measure of that dark energy. There are other theories, I will not talk about them, okay, which are going against the theory that we have discussed, but they don't have any experimental support, okay. So if you don't have an experimental support, your idea cannot be taken forward, but still there are different fields that are working, like some people go with the modified gravity, giving an extra dimension to the gravity, and assuming that there are some extra dimensions, what we call string theory, okay? Maybe they can be the candidates, but you cannot test them in the laboratory. As I said, you have three important testing equations. You test them in your laboratory. So they are giving you the idea. Now talking about the universe, this is not the whole universe. It's wrongly written here. It is observable universe. Only the universe that we can see, okay? What is beyond that, we don't know, because that light will never reach us, okay? So, dark energy, you see, its percentage is extremely large, 68%. Dark matter is 27%. And the ordinary matter, what we call ordinary, that you can see in the sky, that means when you open your eyes in the dark night towards the sky, you are not seeing the mysteries of the sky. There are these light dots existing in the space, but they are not the actuality of that space. And you are a part of that ordinary matter, that's only 5%. So this is a pie chart and giving you a clear idea about the composition of the matter in the universe, and you can see the role of dark matter is extremely large. So dark matter and dark energy shape our universe but remain unresolved mysteries. Because we don't directly detect them. So you have a detector, you can completely detect, and you say, come on, this dark matter is made of the particles A, B, C, and D. That's not the case. But we infer their presence. We cannot explain the visible universe without these things being out there. Now, a very first question to you. I want your involvement in these questions. We talked about it, okay? So the question number first that I'm asking you, when you look at the night sky, do you think what you see is the whole universe? Or could there be more than that is hidden from us? So what is the reasons for that?
Because the earth is constantly expanding and we are not able to.
You can speak loud because the universe is constantly, okay, right. Yeah, you? Okay. So you know the answer to this question. Now, if the galaxies do not move away, the way Newton's laws predict, what are our two options as physicists?
The first option is the dark matter, which is almost to the 67% of the universe.
Exactly.
Okay,
it doesn't matter, plus minus can happen.
Another is dark energy.
Yeah.
And the first one is dark matter.
Exactly, right? Okay, if you had to design an experiment, how would you detect something invisible like dark matter?
I think there is also going an experiment that's known as LIGO, if I'm not wrong.
Yeah.
That actually detects the gravitational background radiation, which actually tells us that there has been some expansion or some collisions of the stars that has happened in the past.
Right, but that gives you the detection of gravitational waves. Yeah? So that you are talking about the gravitational waves, but I'm telling you here that how can you design an experiment? So your experiment will simply be an observation, okay? You would like to see the light bending in the in vicinity of the galaxy. You would like to measure the speed of the stars that are lying on the periphery of the galaxy. So your laboratory will be only that. Okay, you can develop your laboratory in that sense. Now, which of these would convince you more strongly? Stars moving too fast or light bending too much?
Light bending too much.
Because the dark matter.
I think both.
Both.
Because you can take light bending as more evidence, but at the same time, if you want to support that evidence, the idea of moving too fast is also supporting the idea of dark matter. Now, if dark matter didn't exist, what would happen to galaxies over billions of years?
The expansion of the galaxy will suddenly stop.
Exactly.
It will.
The expansion of the universe will not be like this. Okay, you may not have a universe the way you see it right now. So there has to have these hidden physical quantities to exist inside the universe. If you looked at a galaxy cluster with strong lensing, what would you expect to see now? You would expect to see the dark matter. Okay? So your laboratory should shift towards sensitizing your equipment so that they can detect that extra mass that is there in vicinity of that galaxy, by virtue of which the bending of the light is going strong. Okay, now if the early universe had no dark matter, again saying, how would today's universe look? See, I'm saying only the dark matter. Maybe it would not exist because you don't have sufficient gravity to hold it. You think in terms of only dark energy. So maybe you could not see even the sky, the spots in the sky during the night. Which candidate do you think is more likely, exotic new particles or hidden black holes, and why? What do you expect? do you expect that there are some additional particles existing in the universe that can be attributed to the existence of the dark matter, or some hidden black holes? Which you prefer more?
Sir, I think exerting new particles, because we know the universe is expanding, so there must be particles rather than black hole, which is attracting.
Universe is expanding, and you are adding space to the universe, and space is made of particles. What you call as vacuum is not a vacuum. Okay? There is consistently creation and annihilation of particles in the vacuum. So your answer is more precise. Exotic new particles, they will have the more contribution. Now, if gravity always pulls things together, how could the universe expand faster and faster?
Again, dark matter and dark energy.
Very good. If a supernova looks dimmer than expected, what does that mean about its distance?
It means it is really far away from the.
It's moving faster. Very good. Why do you think we need 3 types of evidences, not just one? As you said a couple of minutes before. Because you cannot directly detect it. So adding more experimental support, which is again indirect in nature, it helps us to have more faith in what we are talking about. If empty space is energy, what happens when more space is created during the expansion? I said it. Yeah, what happens?
New particles are continuously added.
You consistently, if you're adding more and more vacuum to the universe, you are adding more particles to the universe. No doubt they are creating and annihilating in a very, very short span of time, consistent with Heisenberg's uncertainty principle. Now, if you had to bet, do you think dark energy is real, or is it a sign that Einstein's equations need revision? See, as a human being, you have no idea about it, okay? But as experimentalists, as theoreticians, we always have a reason. We always have a reason to think that there is dark energy. Otherwise, sending a rocket to the Mars would have been a failure. Sending a satellite to orbit the Earth's orbit would have been a failure, right? So you are in more and more search of experimental support. But what you observe it. It's a reality that the universe is expanding, and it's expanding very fast. And universal law of gravitation is not consistent with it, isn't it? Right? So the point is that it again goes to it falls in your own framework, what you will, whether you will believe it or not. So you see, we are not talking religion here, we're talking science. And science here is based on evidence. And religion is based on the faith, okay? So here you certainly have a reason. You have a reason to at least believe that there should exist dark energy. Dark energy should be real. How does it make you feel to know that everything we understand is less than 5% of the reality? Because only 5% of the universe is observable. So that's why only that 5% to you is a reality. Because you can see it, okay? You can see it not with the naked eyes, you can see it with the telescopes. Because there is involvement of the electromagnetic radiation, which is not the case when you talk about the dark matter and dark energy, right? So I think this should be, so if we eventually solve the mysteries of the dark matter, how will that change the physics? Your arguments, these are the questions for you. Yes?
That does mean that the gravitation of the Newton will hold.
okay, you're right, the physics that we have done till now is holding and everything is going right, and then you may go into the domain of multiverse, you will leave this universe, you'll be thinking about the other universes which may be existing parallel to us, consistent with string theory. So with this, I would like to stop this presentation. I hope you find it fine, at least some state of brainstorming. Okay, so a very goodbye to all of you.
Thank you, sir.